So welcome to our first session. Now this is when things get serious. No more fun, no more games. The 10-minute timer is going to be very sharp. The 3-minute timer is going to be very sharp. So this is when we actually start getting students and postdocs presenting. And everybody who's presented today will be eligible for one of the awards for Best 10-Minute Presentation or Best 3-Minute Pitch. There will be 2 awards in each category. And to judge those awards, we have a panel of illustrious judges who are sitting over here, who are now going to be, unfortunately the camera can't point at them, but I will now introduce them. We have Jennifer Bodden from TELUS World of Science Edmonton. She is the science director there. We have John Bell, who is the International Research Officer for our Vice President of Research Office. And we have Michelle Prue, who is the Executive Director of News and Media Relations and the editor of Folio. Now, these judges, please clap for them. Come on, make them feel as awkward as possible. You'll notice that these judges are not technical, they're not engineers, they're not scientists. They are here to really sort of view these presentations from the perspective that they would in their professions, which is they deal with experts, academic experts, research experts all the time, but with a different view, whether that's doing public outreach and education, whether that's writing news, or whether that's setting up international partnerships. And so they're going to look at all of our presentations through that lens of how effectively are our grad students and our postdocs communicating their research to folks who don't necessarily have the same technical background that they do. And so throughout the day, they will be making marks, and then at the very end of the day, when we announce the winners of the Best Poster competition, by the way, did anybody vote for Best Poster yet, or is everybody biding their time? Good, bide your time. See all the posters. So we'll announce all the winners at the end of the day. So again, you got to stick around, dip into that coffee. So our first session, Enhancing Current Energy Systems. We're looking a lot at research here that's to do with our current energy system that is really based on hydrocarbons. And so we'll have 3 10-minute presentations, 3 3-minute pitches, and I will introduce each individual speaker to come to the podium and then get things started. So to start our first 10-minute presentation is Orain Brown from our theme Heavy Oil Partial Upgrading. Orain?
All right, thank you very much for that introduction. And as I say, we're looking at a low-cost catalyst for desulfurization and some biomass conversion. This is a multidisciplinary project team based here at the U of A, but we also have some collaborators at the University of Calgary. But to get right into our presentation, if we lived through the last provincial election, you'll know that it's all about pipelines. In fact, if you want to solve world hunger or achieve world peace, you know we need more pipelines. But on a more serious note, pipelines are really important, but they only tell half of the story. Because to get Alberta bitumen from the mine site to either tankers or refineries, we need to get in the pipeline, but the bitumen we get from Alberta is not really pipeline quality because of the density and the viscosity. And so it has to be undergo some processing. And there are 2 things that can be done. One is that you can dilute the bitumen with a solvent and then put that diluted bitumen into the pipeline, or it can undergo some upgrading to make synthetic crude that will flow in a pipeline. And there are some challenges associated with both upgrading and dilution. And so an alternative is to go a route that's called partial upgrading. And essentially what we want to do is to take bitumen, and there's a schematic of it on the screen here, and essentially deaggregate it. And there are a lot of approaches we can take to deaggregating bitumen, but one of the most useful approaches is to either add hydrogen or remove sulfur from some of the organosulfur molecules that are in bitumen. And this is the approach that we want to take towards partial upgrading. And so we want to do this with earth-abundant catalysts, and we want to target molecules that are in the asphaltenes towards deaggregation. So one of the first things that we do is that we've been using iron-based catalysts to do partial hydrogenation of polycyclic aromatic molecules in asphaltenes. And the molecule we're using here as a target is pyrene, and we are able to get some partial hydrogenation of pyrene. But the bulk of our research focuses on desulfurization using nickel catalyst. And nickel alone is not very effective for low temperature hydrodesulfurization, But if we add a potassium salt as an additive, what we find is a dramatic improvement in our desulfurization yield. And I should point out that the potassium salt does not work on its own, so you do need a combination of both nickel and potassium for effective desulfurization. Now, potassium effect is very unique, and we've surveyed quite a few alkali metal ions that are in the same group as potassium. And what we find is that potassium really does give us the best combination of high conversions and high desulfurization yields. And the reason for that is we think that the potassium binds to the aromatic group of the dibenzothiophene as well as the sulfur, so it weakens the carbon-sulfur bond and makes it more susceptible to cleavage. And secondly, once that sulfur is on the transition metal atom, in this case nickel, the sulfur assists with removing the potassium assists with removing the sulfur from the surface of the transition metal, thus allowing us to turn over a catalyst and continue our desulfurization. Now, our reactions can proceed at fairly mild conditions. So if we back off the temperature, go to 150 degrees instead of 175, and cut the reaction time in half, we do get a significant drop in our conversion, in this case 37% conversion. But what this allows is for us to evaluate the effect of a second metal on our catalysis. So if you turn your attention to this graph, what we find is that at these mild conditions, nickel alone gives just about 37% desulfurization. But if we add a second metal, in this case copper, as a co-catalyst, we're able to increase our conversion significantly in that second bar. And probably more important for us is that using this nickel-copper potassium system, we're able to take the hydrogen pressures down to 1 atmosphere. This is unheard of in hydroprocessing, and still get some amount of desulfurization. And if we want to improve our efficiency, we can stay at 1 atmosphere of hydrogen and simply increase our processing temperature to 200 degrees, and we have a fairly efficient system. And so we're continuing to do some work on this. I should point out that there are some challenges in this area, in that the potassium additive that we use is certainly the key to achieving efficient desulfurization. But what we're using now is a slightly expensive additive, potassium tertiary butoxide. And so we're working on switching to potassium hydroxide as a much less expensive source of potassium. And in addition, we're working at recycling our potassium, so we're not adding fresh potassium to the system each time, but we can have a recycling of our existing potassium source. At this point, we're going to switch gears a bit, in that, we are certainly looking at partial upgrading of heavy oil, but, we're in the future energy systems area, and so we want to look to the future. And we think biomass really holds quite a bit of potential as a source of hydrocarbons, both for fuel and petrochemicals in the future. And so we're looking at depolymerization of biomass to give small organic molecules. And the key to this is to understanding the structure of biomass. And there's some very key linkages that hold things like lignin together in biomass, and the linkages are shown here. And the idea is that if we can selectively cleave those linkages highlighted in red, then we can depolymerize biomass and be on the way to getting essentially a renewable source of petrochemicals. The linkage on the left I'm going to focus on, because this accounts for the vast majority of all linkages in biomass. And so if we can cleave this linkage, we're essentially halfway there in our drive to depolymerize biomass into useful fuels. Now, the approach that's generally taken in this area is that we take a beta-O4 model compound, as is shown on the screen here, and we do 2 steps. The first is that we oxidize it, so we remove hydrogen from this benzylic position that's shown there. And then the second step is that we reintroduce hydrogen using a second catalyst into the system, and that cleaves the bond that we desire. And we tried to do this with a copper catalyst that we designed in-house, And essentially what we wanted to do is essentially in the first step, we would do dehydrogenation, and then in the second step, we would do hydrogenolysis. But we found that this didn't work at all. And in fact, and to our delight, is that in one step, we can essentially remove hydrogen from our model compound and then recycle that hydrogen for the cleavage of the bond that we desire. So we don't have to add hydrogen to the system. The molecule serves as a source of its own hydrogen. And this is not limited to just the simple model compound I showed earlier. But if we go to this more complex model compound with 2 hydroxyl groups, the system is still fairly efficient at borrowing hydrogen either from this benzylic position or this primary alcohol to effect the cleavage of this carbon-oxygen bond to give us our desired compounds. I should point out that in addition to borrowing hydrogen from the actual molecule we're interested in cleaving, we can use a completely independent alcohol. In this case, we're using isopropanol, and we can take hydrogen from isopropanol and use that hydrogen to cleave the carbon-oxygen bond that we are interested in. And this is a very useful point, because when we go to now polymeric model compounds, in this case, this polymer that's on screen here, we can use isopropanol as a source of hydrogen to effect essentially a depolymerization of this polymeric compound. And this is important because in the absence of isopropanol, so when we just are abstracting hydrogen from the actual polymer, what we find is that our efficiency is slightly less, because once we dehydrogenate, the polymer becomes insoluble and falls out of solution. And so isopropanol certainly helps in that regard. Probably the marquee result for us is that we can take now actual lignin samples and with isopropanol, and we're able to extract some small molecules out of lignin, showing that our attempts to depolymerize lignin are certainly moving in the right direction. So to summarize, what we've done is that in the partial upgrading field, we have made some successes in both partial hydrogenation and desulfurization. And finally, we're doing some work in the depolymerization of biomass under fairly mild reaction conditions. And that's just about the end, so I'll just end by acknowledging quite a few of my coworkers who work with me on this project. Thank you very much.
Thank you very much, Arain. So our next presentation, Najmuddin Sibawehi is working in our heavy oil in situ theme, and he'll take it from here.
Thank you very much. I'll be presenting on real-time steam allocation workflow using machine learning for digital heavy oil reservoirs. In my presentation, I'll give a background on what we are doing, previous work, what others have done, then the research problem, and the workflow that we came up with. Basically, in heavy oil, what we try to do is inject steam in order to reduce the viscosity of the heavy oil so that we can produce it. So in this case, we are trying to, our model that what we are trying to work on, the workflow that we are presenting is for SAGD. So where you inject steam in the top well, then it produces at the bottom. So over the years, various researchers have tried to work on this and how to improve on what they call the performance of steam allocation. So basically, we have the earlier one where they use first principle models, and they try to change the injection rate or the steam generating capacity or steam quality in order to improve their MPV or any other performance indicators they are using. Another case also is that you try to improve the performance by monitoring the temperature and base your decisions on it and say, okay, I'm going to change my rate or change this to this. Another way also is there also real-time approach which has also been used, which using as shown in that diagram there. But the problem sometimes you are faced with is we have this issue of when you are using the first principle model, the time it takes to run, it takes very long time. It's computationally expensive. Updating it is also very, very expensive. So in the past, people have also used, tried to use some analytical models to try to use it to represent the reservoir. But one of the challenges also they are also facing is like they are using a static model to represent a dynamic system. So since our first principle model is based on a dynamic system, so what we try to do is come up with a dynamic model which is easy to be updated to represent our reservoir, to use it in our prediction. One other question we also want to answer is we want to do a short-term prediction, not a long-term prediction, which is one of the challenges with the first principle models. So now the question is, we want to find a way to dynamically and intelligently allocate our steam in order to improve our net present value. So to demonstrate what we have done, we use this basic reservoir with those blue. This is the distribution of the permeability in the reservoir with 3 well pairs. So here, the blue indicates what they call, these are the low permeability sections, which is still distributed in the reservoir. So here, first, we need something to represent our dynamic model. So we are using system identification model. In the system identification model, we are using, we are trying to predict what happens next, or our production rate, what will happen in the future, based on our past injection and our past production rate. So we use a polynomial to represent it. So the polynomial is the one we are going to. So the polynomial is dependent on it's a time series. So to do that, we have to get some data and try to run several, runs to match our model. In matching, we use, we run like 350 models. And in the end, what we notice that our model is able to predict for 1 month, so which gives us confidence in using that model for our next prediction. Because what we try to do is the model should be able to have a very good prediction performance longer than what we are going to use it for. So here, basically, just to simplify, so we want to find what happens in the future based on the past history. So here, what we are doing in the optimization is we try to maximize our MPV. So we try to play with the injection rate of different wells at different times. So to do that, we use 4 cases to represent what happens in the reservoir. First case is the case of where we have all available steam, which means our steam generator is able to produce. It's able to produce at its full capacity for the period we are trying to optimize. The second case is we have a use that requires steam. It may be that we have we are unable to use the full steam, so we are trying to see what happens if you optimize by that. Another one is the random steam generation capacity, which that one is basically based on your steam generator is not really performing. Sometimes it's moved up and down, so you want to try to see, if my steam generation changed for this prediction horizon, am I able to optimize it? Okay. Then the last one is we are trying to say, we have the steam generation and we also have the wells we are allocating it. So how effective is it going to be if I optimize both my steam generation and also the allocation I'm doing to the wells? Okay, so here to do this, the workflow that we came up with. So first, we start with you acquire the data, because we don't have a real reservoir, so we have to use a digital reservoir to represent the real reservoir. So you acquire the data, then you do the train, which I earlier demonstrated. So now before you start this prediction, the prediction horizon is for 7 days. So first question you have to ask yourself is, there are 2 options we have here. We are going to be using the cumulative MPV to make the decision for the next step. So the first one is are you going to, at each stage of the prediction horizon, are you going to make any changes to your system? No. So that one we demonstrate, we show it. The second one is, in this case, is because we are trying to use the cumulative MPV to make the decision. We might not know that if a particular well is not performing or not the other. Or maybe if we have to present. So what it does is that at each stage, we try to find the individual MPV, which one is individual MPV for each well, so that we determine the performance of each individual well in the whole well part. And based on that, if that well is not performing, we will say that, then since we have this amount of steam to be distributed within this period, these wells are performing more, so redistribute that steam to those particular wells. This basically also is applied in the commercial simulators. You do that at each time, you try to check your productivity index. Based on that, you can allocate this amount of production or injection to a particular well based on this productivity index at each particular time. So one way we came up with this step is to kind of replicate that scenario which happens in our commercial simulator. Okay, so now, the two cases I showed, the first one is basically that happens in our normal commercial simulators, which is the CMOS optimization software. So what we did here is like after optimization, you realize that the system is not able to detect that, okay, if one particular well is performing or not the other. So if you see the well 3, you realize that the MPV is going towards what? Negative. How do we improve on that? So the next scenario here, we are going to be checking the individual MPV to see which well is not performing. So if you see that, you realize that for the well 3, it drops the rate. So what you do is we reduce the amount of allocation to it. So in the end, if you compare the two, you realize that the MPV for this scenario increased by what? 1 million, which shows that to do just that simple change, we can improve our net present value. Okay, basically, so this is just a summary of the results. So if you look at the scenario 1 is the first case where you don't make intervention. The scenario 2 is the one that you are going to be checking the individual MPV to see what is happening. So in case there's something wrong, you can check and improve the MPV. So if you realize in all cases, we realize that the MPV for the scenario 2 was higher, more than because this one was compared with a base case. The base case is just basically a constant injection period. If I do a constant injection for the whole optimization cycle. So if you compare with it, you realize that the scenario 2 keeps having higher MPV than the first case. Okay, in summary, what you realize that is in both scenarios, we had our MPV increasing between 25 to 50%, and we realize that the computational time for the SIM allocation reduces significantly. And the advantage of this workflow is that we can easily update our model, and which can be easily integrated in the field, because this doesn't involve any complicated things. So those at the field can easily understand what is going on. So the proposed workflow it makes it easier for us to make a decision. I'd like to acknowledge our partners in this. Thank you very much.
Thank you very much. So we'll get the clock reset. Sorry, I turned us over too quickly last time. We need to give a second for the clock to reset, for the judges to finish making their comments, so I just have to stand here and entertain you. I always find it, and sorry, many of you know me, but my role at Future Energy Systems is to actually talk to many of you and write stories about what you do, and I always find the process modeling stuff quite interesting. I know I've talked to folks in carbon capture about it, and it's always interesting to see how you can use modeling to try and understand what steps you take, and if you change the order of steps to try and make things more efficient. And so we do it in a lot of different areas. You're going to hear about some of it with respect to other things, renewables, and other types of technologies throughout the day. But thank you for that. I'm just watching the judges. We're good to go. Okay, the judges are ready. So time for our next 10-minute presentation. In fact, our final 10-minute presentation for this session. I will invite up Reza Kalkali.
Good morning. My name is Reza Kalkali. I'm an MSc student in chemical engineering, and I'll be presenting my research results on role of bitumen water and fines content on solvent removal from non-aqueous extraction Gangue. Before that, I would like to make a quick introduction on what we're doing and why we're doing it. So we all know that oil sands is a mixture of bitumen, mineral solids, and water. And what we're looking here is bitumen, and every extraction process is looking forward to separate bitumen from mineral solids and water as a valuable product here. But the current commercial methods that are being used use either hot water or steam to liberate bitumen from the mineral solids, which has its own problems. Two of the main problems are the high heat consumption, and tailing ponds, the famous trouble of tailing ponds, which both are created because of the presence of water. So here is solvent extraction, non-aqueous extraction or solvent-based extractions is being proposed, which simply proposes to remove water from the process and use a solvent to dissolve bitumen and separate it from fine solids. With all the advantages of this method, it has its own challenges that need to be addressed. One of which is the gangue, the waste material that we end up here. So instead of tailing ponds, we end up with a mixture of mineral solids, water, and a good amount of solvent that needs to be removed before leaving the gangue into the environment, which is not a good thing, both financially and environmentally. So the solvent, to remove this solvent, we can think of different ways. One of which has been proposed in the literature is washing the solvent with a kind of solution, which we think that has its own complications, because if you try to wash this solvent out of the system, you either do it with a water-based solution, which means introducing water again into the system, which doesn't make sense, or using another solvent, which will make you deal with another solvent in the mixture from the first place. So the other solution, which looks much simpler, is just to let the solvent evaporate and come out of the mixture in a gaseous state. And this evaporation, the rate of evaporation needs to be investigated. There are several parameters that are effective here, and many of them have been studied before, like temperature, pressure, or bed height. And within our group and in my study, I did investigate the role of residual bitumen, water, and fines content on the evaporation rate of solvent from the gangue. To investigate that, there is one problem, and that's the gangue. The gangue's composition is different after each extraction. So in order to investigate that, we need to be able to control the composition of the gangue. Here is where an idea has been developed within our group, and it's to artificially make a gangue that can mimic the characteristics of a real gangue. But in this way, we can control the composition of the gangue, and we call it the reconstituted gangue. And here's a quick review on how we make it. So you take an OSAN, or you perform a Dinstark extraction on it. You end up with a bitumen solution, solids, and water. You basically separate all the components. Then you get the bitumen. You mix the bitumen and solids to your to the content of your favor, and you mix them. Then you let the solvent dry to get bitumen-coated solids. Then you add water and to the bitumen-coated solids. You mix them again. Then you add solvent, which is cyclohexane here, and you mix them again. At the end, you end up with your gangue, the reconstituted gangue. You can pack it into a dish and put it on a scale, which is connected to a computer, so you can monitor the weight loss and kind of investigate the evaporation. So if you look at, this case is the general case of our study is a porous media being dried out. If you put a porous media, a wet porous medium, to dry out, you end up with a curve like this, where on the vertical axis, on y-axis, you have the cumulative mass loss, and on the x-axis, you have time. So if you look at this plot, there are 3 stages. One is the fast initial evaporation stage, then you have a transition stage, then you end up with a final stage, which is a lot slower than the initial stage. The initial stage, the fast drying of the initial stage, has been attributed to the liquid film connectivity within the pores of the porous medium. If you, and in the beginning of drying, there is enough liquid, there is enough solvent in the porous medium that this, is this the, okay. So there is, this liquid film is formed into the pores of the medium due to capillary forces. And this acts like a pump, pushing the solvent, the liquid, from the bottom of the sample up to the surface, where it can evaporate from the surface, which is kind of like a pure liquid just evaporating. And that's why the initial stage is so fast. In the transition state, the area of surface evaporation is limited, and that's why the evaporation rate gets reduced. And in the final stage, the wetting front has receded into the sample. The solvent needs to evaporate in the sample, in the pores, which we know takes a lot more energy. And it needs to diffuse out of the pores in gaseous state, which is a slow step. And that's why, that explains the much slower evaporation rate in the final state. It has been shown in the literature before that the first stage, the initial stage, is that evaporation is dominated by solvent evaporation. And the final stage is dominated by water evaporation. And because we are looking to make solvent evaporate faster here, we take a look at the initial stage, and that's the stage that we are looking for to make faster. So to move forward, to investigate the role of bitumen, I made two samples, one with no bitumen and one with 1% bitumen. As you can see, only 1% of bitumen present in the system makes the initial evaporation rate drop by 30%, which is a big number. You may notice that at the final stage, the no bitumen sample falls below the 1% bitumen. But it should be noted that the final stage is dominated by water evaporation. So the initial evaporation stage is where we are looking for, we care about for solvent evaporation. As a role of water, I had several samples with 3% water, 6% no water, and 12% water. It's interesting to see that, well, we knew that if you increase the amount of water than connate water, the 3.7%, which is inherently present in the sample in oil sands, the evaporation rate drops. But it's interesting to see that if you remove water from the system, if you dry out your sample before, if you dry out the oil sand ore before you perform the extraction, the evaporation rate still drops. So it means that a little bit of water in the system is helping the evaporation of solvent. And at the end, for the role of fines, increasing the fines content from 8% to 16% caused a drop in the initial evaporation rate, which was expected, as we knew this before in these studies. But again, removing the fines out of the sample caused a slight drop in the evaporation rate again, but it wasn't as big as the effect of water. For conclusion, residual bitumen has the most significant effect on the evaporation of solvent. Water has an optimal effect. More than 6% makes the initial, okay, my time's up. Should I stop or?
Yeah, you should stop.
Okay. More than 6% of water makes the evaporation rate drop, but less than 3% makes the evaporation rate drops again. And fines don't have that big a role, but having more fines, higher content of fines, make the evaporation rate drop. Thank you very much.
Thank you for that. Sorry to be the guy in the tie who just sort of wanders towards the podium as the time runs out, but somebody's got to do it. So with that presentation, we're done with 10-minute presentations for this session, and now we have to transition to the 3-minute pitches. Now, how many people in this room have been exposed to 3MT or to falling walls? Put your hands up. Anybody done 3MT, falling walls? A lot of people on that side, some people over here. As you know, it is a very different discipline than giving a 10-minute talk. It's not that 3 minutes is less than 10 minutes and therefore it's easier. In fact, some would argue it is much more difficult because you've got 3 minutes to try and get your point across. And so for all of our people today who have opted to do 3-minute theses, or 3-minute pitches as we're calling them, I thank you in advance for participating. And we'll get the clock ready for 3 minutes. Judges, are you ready to go? Can I get a thumbs up? Judges all set. Jose Guevara is going to start us off for the 3-minute pitches, and we'll be very sharp on the time here. So get in, get situated, and then we'll start the clock.
Thank you. Okay, so today I'm going to talk about steam injection optimization using reinforcement learning. So in SAGD, the objective is to have 2 horizontal parallel wells in which you inject steam through the top well, and hopefully this steam is going to decrease the viscosity of the oil and allow it to be produced in the lower well. Okay? So in general, the major challenge of this process is that at what rate are you going to inject the steam at? Okay, so typically this is injected at a constant rate, but this is not necessarily the best case. So the main issues for this is that the dynamics of the phenomenon is very highly complex. The effective injection rate may be significantly delayed. So what I inject today, I'm only going to see the results of it tomorrow, or 2 days later, or 3 days later. Sometimes it would be maybe even better to sacrifice immediate production for long-term optimization. And the fact that in real scenarios, which you have multiple wells, the limited amount of steam, the steam available is limited. So you want to distribute it optimally through all the well paths. Okay? So what we are proposing is to use a reinforcement learning scheme. Okay? So in this scheme, the objective is that you want to train an agent by continuous interactions with the reservoir, or with the reservoir model in our case. And through continuous interactions with this model, you are able to eventually train this agent to behave optimally and hopefully optimize long-term cumulative performance, which could be net present value or oil recovery or whatever. Okay? So at every time step, the agent is forced to take an action. So this action can be increased steam, decreased steam, or something else. And in return, after one time step, after you apply this action, the environment or the reservoir is going to offer you a reward and is going to change the state. So based on these interactions between rewards, state, and actions, the agent is hopefully going to learn how to behave optimally. And again, so the main thing here is that you want to behave optimally in the long-term scenario. So you want to maximize a specific performance measure, a cumulative performance measure over the period of production, which could be 5 years, it could be 10 years. So it's not short-term optimization, unlike traditional works that have been done in this area. So the final result is that you're going to have a profile of steam injection. So you want to find out what is the rate, the optimal injection rate at every time step during 5 years, during 10 years, or 20 years. And hopefully, once you get this optimal steam injection profile, you are able to make some physical conclusions as to, and to explain why this profile is optimal and what are the physical laws behind this profile. Thank you.
Thank you very much. Right on time. All right, so on to our second 3-minute pitch for this session. I will welcome up Raising from our system-wide theme. And once again, we'll just make sure you're set, and then we'll get this clock started.
Thank you. So our study is about the development of modeling oil sands production in an integrated assessment model, energy consumption, CO2 emission. So basically, in this study, we use this global change assessment model, GCAM. It's an integrated multi-sector model that explores both human and Earth system dynamics. Here we have a energy flow for GCAM, which emphasizes on the unconventional oil sands module. We can see that energy flows from primary energy like oil sands to energy transformation sector. So then we have this process of oil sands production, including extraction and upgrading, and then to treated unconventional oil. And then they flow to distribution system, and eventually they will go to final demand. And here is the specific detailed energy flow for oil sands production. So in the original GCAM model, there's only like inputs as oil sands and natural gas. And the output of this system is synthetic crude oil. And there in between, there was only one single technology called unconventional oil production. And in our study, we've added like diesel, oil, and electricity, fuel gas as energy input. And we've also divided this process into extraction and upgrading. So here we have some preliminary results from our study, including energy consumption and CO2 emission. So actually, there is a series of future assumptions, such like GDP increase and population and other indicators. So under this specific consumption, our results shows that energy input will be tripled by 2050 due to the increase of oil sands production. But still, so you can see here our base year is 2015, and we're still calibrating the base year results. And in this figure, the top row is extraction and bottom row is upgrading. And on the right side, you have the figures for CO2 emission, and we can see that cogeneration technologies result in much lower CO2 emission, and also large emissions caused by diesel oil combustion from the extraction process. Thank you.
Thank you, Ray. And so we're just about on time. We're only running 2 minutes late, which is pretty impressive since I'm emceeing. I'm usually pretty late. Anyway, I'm just seeing the judges scribbling quickly, so I'm gradually going to invite Fabiano Domingos to rise, and he's going to close us off with our final 3-minute pitch for this session, and then I'll be back to say more things. So again, Fabiano, let us know when you're ready, and we'll hit the clock.
Good morning, everyone. My name is Fabiano Domingos, and today I will show you a revolutionary, reliable, and cheaper method to power sensors in a SAGD line. Sensors are basically everywhere nowadays, from the thermometer that we use to measure our kids' temperature to motion sensors that open automatic doors for us. And in the oil industry, that's not different. For example, an impressive amount of sensors is required to monitor and operate safely a pipeline. In Canada, SAGD is one of the main methods for heavy oil production. Basically, we use steam to reduce the viscosity of the heavy oil so we can extract it through a pipe. These SAGD lines require multiple real-time sensors to monitor temperature, pressure, corrosion, leaks, and so on. The first problem that we are trying to address is that conventional wireless technologies cannot be applied to sensors in the SAGD environment. Basically, your wireless signal cannot reach deep down in the ground. The second problem is that the current approaches, they use really long fiber optic cables over the entire length of your pipe, which means that these cables are extremely fragile and they are also costly. So, if wireless sensors do not work, and sensors with cables are not the best option for the oil industry, how do we come up with a better solution? The answer is using the pipe itself. Our technology is a viable solution because It removes the cables completely, and we don't have to worry about that. Our solution creates a standing wave on top of the pipe and uses the metallic pipe itself as a way to transfer power and data to our sensors. While most of the wireless power transfer techniques suffer from having this metal, our technology actually uses that metal as a way to enhance power delivery and data communication to the sensors in the SEGD well. Therefore, with our technology, we can use as many sensors as we want in any place that we need without having to worry about cables and wires. Ultimately, with our technology, we can have more precise monitoring of oil production because we can have more sensors, ultimately leading to more efficiency and lower environmental impact. Thank you very much.
How about that? Done with 25 seconds to spare. Thank you, Fabiano. So with that, we're done with our first session. This is our presentations that have been about the current energy system. Please, one collective round of applause for everybody who presented. Not only are they doing important work, but they had the unenviable task of being the first ones to have to go through this process. I know that some of you are presenting in the next session, and you get a sense of what you're in for. I'm just going to do one thing. I said that we don't have any scientists on our panel. I'm sorry, Jen. Jen, of course, is a scientist by background at TELUS World of Science. It would be very weird if their science director wasn't a scientist. But she does deal with public education a great deal. Anyway, so next steps. We've got a break. We're back here at 11:15. During this break, all of the people who have a red hexagon on their tag are required to be at their posters. They're going to be out there talking about the research they're doing related to heavy oil and the responsible development of it, of hydrocarbon resources. So by all means, please go out there and take a look at their posters, have a chat with them, and maybe consider voting. But I do recommend that you wait through the day and see all the posters before you make that vote. It's going to be very important. See you back here at 11:15.